Okay, let's start. I guess you have some questions. Before we do that, I just want to say one thing. I got a lot of suggestions already for topics you wanted me to cover, which I had not planned to cover. So I added about 30 slides, which means somewhere I'll have to remove some. And so I'm going to cover a bunch of topics either today or tomorrow that I had not planned to cover. Also, I want to say one thing. Yesterday, I think the lecture was pretty much things you knew. Today, I think it will be different stuff. But even if you know it, my way of thinking about it is sometimes different than other people's because I'm strange. And so maybe you'll learn something just from seeing it from a different perspective. Okay, Maria, how does this work with the questions?
First, for the questions, you should push the button, the red button in your microphone, and I think they should start. Maybe Basil, if he can prepare, or someone should start, and we don't need to have any order. So, who is ready?
Somebody ask a question.
Yeah, first question. In the independent particle model, there seems to be no difference between acting a proton or a neutron to an orbit. So from this we could expect maybe neutron only or proton only nuclei. Why are they never observed?
Well, you do have proton only nuclei. Hydrogen.
Yeah, like for more.
Okay, that has to do with, it's actually a very subtle question. The deuteron exists. It has a neutron and a proton. The diproton, two protons, and dineutron don't exist. And that is a subtle effect of the Pauli principle, which I could maybe make a slide for tomorrow to show you. And then as you build up light nuclei, you get the lowest energy if you have equal numbers of protons and neutrons. And I think you can see that. You have the lowest level in the potential well, and let's say I put 2 protons and 2 neutrons in it. And then the next level, let's say I put 2 in, and the next level 2. If I add up all those energies, that energy is less than if I put 2, 2, 2, 2, 2. Right? Is that clear? So the energy of a system with equal numbers of protons and neutrons will be lower than the energy of one with all protons or all neutrons. And that extra energy is enough to make them unbound.
And is that just an empirical fact?
More or less, yes. I mean, some theories reproduce it, but when theorists know the data, they tend to do very well. When you get to heavier nuclei, then you have, remember I showed the Valley stability curves, then you have Coulomb effects coming in, okay, which change the relative numbers of protons and neutrons. But it's basically that equal number, since you fill the wells, the potential wells separately, having equal numbers gives you a lower overall energy. Okay? So, after the lecture, remind me to put in a slide about the deuteron.
Sure.
Okay, because I'll forget.
And I got a second question as well. To me, the nuclei with matching numbers of nucleons are quite analogous to the noble gases. Still, we don't call the noble gases magic in any way. Are the matching numbers fully understood, or is there still something magic about them still?
Well, they're very magic. I showed you last time how you can take a square well or harmonic oscillator, modify the shape a little, put in a spin orbit force, and reproduce the magic numbers. So, in a sense, that means we understand the magic numbers. Now, you can ask the question, why is there a spin orbit force? And that's a very subtle question, and if you look in older textbooks, 20, 30, 40, 50 years ago, you will see all sorts of arguments about why there should be a spin orbit force. All those arguments are wrong, and the answer was realized about 10 years ago. primarily by a guy named Joe Ginocchio, but also some theorists like Peter Reed and others, who realized that it's a consequence of the Dirac equation and the difference in the positive and negative energy solutions. So it's a very subtle effect. But once you accept that there's a spin-orbit force, and you have that you can replace all the interactions by a single box, then you can get the magic numbers. Now, as you will see either today or tomorrow or Friday, the magic numbers, which we think of as these benchmarks that are very robust and apply to all nuclei, in fact change as you go far up stability. And we'll see that, and we'll see why. If you want the answer ahead of time, it's due to the monopole proton-neutron interaction. We'll see that.
Yeah, thanks.
Okay? Other questions?
Okay, maybe I wasn't so... I didn't do my homework, so anyway, I'm going to ask such a question. So, by introducing the spin orbital force, you somehow get rid of you get... Okay, let's think about it. So why do you use negative spin orbital force? So this with the higher spin should go lower, and this with the lower spin should go higher.
Yeah, okay, so let me, does anybody see my cursor? Oh, there it is.
Because I think even if you introduce a positive spin orbital term, I think you might still get the magic numbers.
No, I'll show you why.
Okay.
I just had to get yesterday's slides up. So if you remember when we took a harmonic oscillator, we got magic numbers 2, 8, 20, 40, and then 70. And if we had done the next one, it would have been 112. So 70 has to become 82, and 112 has to become 126. You need something to make that change, right? Clear? Okay. So,
Maybe you could show the slide where you got this transition between harmonic oscillator and what happens when you have this spin orbital term.
no, I want to show a different one. Just give me a second. Excuse me. Why is it skipping from? There we go. Okay, you meant this one. This business of squaring off the potential well so that the higher angular momentum comes lower helps, but it doesn't really help enough. You really need to spin orbit and... okay, so remember we had 2, 8, 20, 40, and 70. Okay, let me actually go back. Yeah, okay, we had 2, 8, 20, 40, and 70. The next shell up will have P a half, P3 halves, F5 halves, F7 halves, H9 halves, H11 halves. Okay? Here we have 70. We want 82. So we want to bring a level down from the next shell into here that can hold 12 particles. The orbit that does that is H11 halves. Okay? So now, let me go back to here. So, what happens is, here's H9 halves. This shell did consist of P a half, P3 halves, F5 halves, F7 halves, H9 halves, H11 halves. By putting in the spin orbit force with the sign that we have it, so that the higher spin comes down, we introduce H11 halves into this shell, you can put 12 particles in there, and that 70 plus 12 gives you 82.
Okay, so
Just let me finish 1 second. For the next shell, I said we would have gotten 112. 126 is 14 more than 112. And what you have to do is bring the I13 halves, which can hold 14 particles, down from the next shell. So that's why you have to have that sign of the spin orbit force. Okay? Next. I thought every single one was supposed to have 2 questions. Yes?
Excuse me, my question simple answer. I didn't attend to the first lecture.
I'm sorry, you did not come to the first lecture?
No,
Okay.
I'm sorry.
Okay.
My question about the nuclear force. I know that it's attractive at relatively large ranges, but across small ranges. And I read somewhere that the reason of the repulsion is the Pauli's exclusion principle, but I thought that was only for fermions. And I don't quite understand how can you explain the repulsion from Pauli's.
Well, okay, let's talk about identical nucleons, like 2 neutrons or 2 protons. Pauli principle says basically they cannot be at the same place at the same time. That means if they get close, something has to push them apart. And so the Pauli principle is equivalent to a repulsive potential at short distances.
So you're saying that it is another type of, it's not Pauli's principle because that's specifically for fermions, but it's the same concept.
Pauli principle applies to fermions. Okay, and so you can think of the Pauli principle as equivalent to a repulsive potential. Now, whether the Pauli principle is a more fundamental thing or the potential is more fundamental, I don't know. That's a philosophical issue, but it has the same effect as if you had a short range repulsive force.
Yeah.
If I understood correctly, the strong forces at larger distances attractive. So I don't get how adding neutrons to an element could make it unstable, as it would only attract more and more.
Oh, okay, because, so your thinking is that if you add neutrons, you're getting more nucleons, they will be more attractive, and it'll be more bound. Is that the idea you're saying? Okay, so there are 2 things. If you remember, we looked at binding energy per nucleon, and we discovered that each nucleon only interacts with about 10 others. Okay, so the total interaction scales as the number of nucleons. So if you add extra neutrons, they're not interacting with everything else. They're only interacting with a few, okay, and the average interaction energy per nucleon stays the same. Okay, so it doesn't help as much as you would think. The other effect, the main effect, is think of the shell model or the independent particle model. You have these orbits at larger and larger radii. The larger the radius, the more weakly bound the orbit is. As you add neutrons, you can't keep putting them into a low orbit because of the Pauli principle. So you have to put them into outer orbits, more outer, and they're less and less bound. Clear?
And
Eventually they're unbound. Okay, it's like, imagine you could only put 1 planet in each orbit around the sun. So you keep adding planets, they're going to have to be further and further out.
Okay, so the second question was
Yeah.
related to the neutron, but it was already asked.
Okay.
So I would like to see the slide next.
About the deuteron?
Yeah.
So one of the 2 of you or both of you, it's your homework or pre-homework to remind me.
Thank you. I'm sorry to be probably a very basic question, but
You're sorry for what?
it will be probably a very basic question.
That's okay.
As you were talking about the magic numbers, you mentioned that they could be double magic, so it's always a magic number per protons or per neutrons.
Yes.
And I was trying to Google it, and it said that there are like separate shells for protons and neutrons. So does it really look like it in the nucleus that they are just separately somehow? What do we know?
Okay. All of this model, this independent tremendous approximation, okay? But the approximation is that the protons fill their orbit separately and the neutrons fill their orbit separately. And so you have magic numbers for protons and neutrons. And they're basically the same magic numbers. The energy levels are a little different. If I did this for protons or neutrons, they would be a little different because of the Coulomb force. Okay, but basically that doesn't change the magic numbers. Now, in real life, you have the neutrons and protons coexisting inside the nucleus and interacting with each other. And so this is a tremendous approximation. And what we'll see, either later today or tomorrow, is that as you add neutrons, the proton energy levels actually change. Excuse me. The proton levels change, and you can actually change the magic numbers. So from 1949 until, let's say, early 1990s, it was pretty much considered that the magic numbers were robust and always there. And excuse me. And the reason for that is that the magic numbers were invented, these numbers, to reproduce the data on nuclei near stability. And those were the only nuclei we had to look at. Starting in the early 90s, not starting in, but really going fast from then on, we began to get further off stability, and we began to discover cases where the magic numbers disappeared and change. And so then we began to realize that there are these other interactions and they can change the magic numbers. You'll see that later today or tomorrow. Yes? Turn yours off. Thank you.
My question was, why so much emphasis put on the magic numbers in nuclear physics?
The reason there's so much emphasis is because if you don't have the magic numbers, and you want to calculate a nucleus with 51 protons, you have to, I'm sorry, just, and you want to calculate a nucleus with 51 protons, you have to take into account all of the interactions of all those 51 protons. If you assume that all these shells are filled and that the excitations of a nucleus with 51 protons is only due to what orbit that last proton lives in, then you've simplified the problem by 50 to 100 orders of magnitude. So, in principle, we don't need them. In practice, we can only solve the problem rigorously with computers up to mass 12 or so, up to carbon. By the way, did you change that 12 to a 6? Okay. Okay, is that?
Yeah. Is there any physical correspondence with the shells, or is it merely just energy? Like, you know, in a hydrogen atom, the electrons take on different shapes, sort of, probability lines. Is there anything?
I'm sorry, I didn't say it again.
Is there any physical meaning behind the shells, or is it?
Behind the word shell?
I mean, behind these nuclear shells.
Well, yes. I mean, if you have a filled shell, you have particles in every magnetic substate allowed by the Pauli principle. And therefore, you have kind of a uniform spherical distribution of nucleon density. And so it is like a shell. It's not rigorously a shell, but it's pretty close.
Thanks.
Yes?
You said yesterday that neutron-rich nuclei are very interesting area of the chart of nuclei. What are the most important physical motivations to study this region?
Okay. I'm not going to answer that, not because I don't like you, but because that's going to be in the last lecture. I'm going to go into some detail about what's special about neutron-rich nuclei. Okay? There's several features, ranging from weak binding to astrophysics to other things. Yes? Turn on the magic button.
All right, here we go. I actually want to go back to this question, just for better understanding this can it be similarly understood with symmetric numbers? The shell, the idea of shells, then for atoms, the electron shells, or like orbitals?
Say the question again.
Is it this idea of shells? Is it similar to the electron shells or electron orbitals?
It's very similar, and it's the reason why in atoms, if you have an alkali atom, you can, for many approximations, treat it as a single electron. And that's exactly the same as taking a nucleus with 51 neutrons and ignoring the other 50. Now, it's an approximation. In the atom, you can excite the electrons in those bound shells, those inert shells, up to higher shells, but it just takes more energy. And same thing in the nucleus. If we want to calculate the properties of the nucleus with 51 or 52 neutrons and calculate states at 10 MeV of excitation, then we clearly have to excite particles from below the shell to above. And so at some excitation energy, the shell, the meaning of the shells kind of disappears. That's typically maybe 30 MeV or so. But for low-lying states, which are more or less, with some exceptions, the only ones we can understand, the shells have a big impact and a big effect. But remember, it's just it's a mental concept which has a basis in reality, namely the occupation of different substates, but it does simplify calculations and understanding tremendously. More? Yes?
Okay, so by introducing this potential, which is the best potential we can get in order to reproduce these magic numbers, I believe it's something more complex than Wood-Saxon.
Okay.
So if you take something like a Wood textbook and see some fancy wave functions calculated by some potential in the short equation, there you have some parameters which you tune for the experiment. So you at least what I mean is that the single part, the independent particle model is working very well near closed shells. So when you have, say, 1 or 2 valence nucleons, but if you, for example, tune them for around 20, is this tune okay for around 50? Is it okay around 82, and so on?
Okay, if I understand your question, the magic numbers, the shape of the potential, whether it's a harmonic oscillator or a square well or Wood-Saxon, has an effect on these energy levels. But a Wood-Saxon potential works as, it's fine. You don't need to go to anything more complicated. If you're a theorist and want to publish some papers, you can add in some extra parameters. But it's really not so necessary. What's much more important is the interactions among the valence nucleons that are not included in the independent particle model. Okay? And we're going to talk about those today. Now, you can think of those as contributing to the potential and make some complicated potential that includes that effect. But you can also do a very good approximation, separate the two effects. A single particle model and then extra interactions. But a Wood-Saxon potential is fine.
No, maybe my question is, okay, so let's take the Wood-Saxon potential which reproduces the magic numbers. But for example, let's say the most simple case, we have a closed shell of neutrons and protons, we have one neutrons, and think of it, okay, so the excited states would be moving up these valence nucleons among the shells, or breaking pair, or going up, or so this potential would depend on some parameters. And those parameters, you can take them from the experiment. So you make some experiment, for example, about 20 closed shell, and you get some parameters. Are those parameters the same parameters for around another closed shell?
Okay, so somebody asked a related question yesterday. They said, I think it was, they asked why thallium doesn't have an 11 halves minus ground state. Who asked that question? He left because he found out the answer to everything he wanted. Okay. Anyway. anyway, he asked why thallium doesn't have an 11s minus ground state. And my answer was, this picture is a picture calculated in a Wood-Saxton or similar potential for a given mass. And you can't say this is the independent particle model levels. These are. Those levels will change as a function of mass. For one thing, if you're talking about protons, the Coulomb force will have a different effect on particles in an H11 orbit and in an S1/2 orbit. And so these relative positions will change as a function of mass. So if I look at this diagram for calcium, or if I look at it for lead, it's going to be a little bit different. Not a lot different, but a little bit different. If any of you had the book by Warren Modelson, there's a nice figure in that book as a function of A, showing how these levels change as a function of A. There's another reason why they change. Remember in the square well, the energy levels go as 1 over the size of the nucleus squared, 1 over T squared. Remember that? Anybody remember that? Remember I took the de Broglie relation and derived that the energy levels in the square well, it was in the square well, go as 1 over the size squared. Okay. So as you go from hydrogen to helium to calcium to lead, the nucleus is getting bigger. Okay? So all these energy levels will change. The size of the nucleus goes up, so all those energies go down. But since an H11 particle lives much more in the outer radii of the nucleus, and an S1/2, where's an S1/2? S1/2 lives more uniformly distributed over the nucleus, the effect of that change in size will be greater or lesser for different orbits. So this picture will change. Now when you read a textbook, they typically say this is the shell model diagram, or this is the independent particle, but that's just not true. Okay?
So this valence particle, so when we feel this shelly decision, I believe it's called the nut or something like that.
I'm sorry?
You call it nut, maybe. If you have a closed shell,
Yeah.
the inner part is called nut.
What?
Core.
Oh, yeah, the core.
Okay, so anyway, but somehow this is confined to itself. So this valence particle, in what potential does it feel? Because maybe this nut is somehow guessing or in it all the forces are like pairing or something like that, because you have this interaction between the forces. So I have this core and I have a valence particle moving around it. What does this particle feel?
In first order, that particle feels the same potential as all the others. Okay, it's just we're filling levels in a box. Whether that box is a square well or a harmonic oscillator or a Wood-Saxton, it's a as you fill that box higher, does the potential change? And we'll see in the last lecture that when you start filling levels right up near the top, where it's almost unbound, the potential itself will change. So you can have that effect, that the last particles can see a different potential than the other ones. But that doesn't occur very much near stability, because they're all pretty well bound in the bottom of the well. Okay?
Okay, half an hour of questions. If listeners have already asked any questions, so if you want to ask something, you prefer to do it tomorrow. Otherwise, I think we have to start the seconds.
Okay. Yeah. I was getting to the point where I was afraid I wouldn't know the answer. Okay, so what we want to discuss today, well, I don't know if you want to discuss it, but I want to discuss it, is, how do I do that? Anyway, are nuclei with more than one valence nucleus. In other words, multi-particle systems. Okay, so this is just to remind you what the question is. These are all nuclei with two particles outside of a doubly magic core, or not is equal. So here's polonium-210 with 126 neutrons, magic, 84 protons, that's 82 plus 2. Here's lead-210, 82 and 128, 82 is magic, 126 is magic, so it has 2 neutrons. Here's tellurium-134 with 82 neutrons, magic, 52 protons, 50 is magic, so it has 2 protons. They all have the same kind of level schemes. Excuse me. Ground state 0 plus, big jump to 2 plus, smaller jumps to 4, 6, and so on. Okay, so that's what we want to understand. Okay, so can we understand that by extending the independent particle model to these multinucleon cases? Now there are 2 issues that come up. The first one is just why these angular momenta. Here we're filling, for example, a 9½ single particle state. Okay, if we have 2 particles with angular momentum 9½ what total angular momenta can they add up to? Well, you could imagine you could have one particle going around the nucleus this way, and the other one going this way, and so you'd have 9½ and 9½, and they would add up to 0. You could imagine they're both going around together. So that would be 9½ and 9½, which would give you spin 9. Well, you don't see a 9 there, so it can't be that simple. So we have to ask the question, what angular momenta are allowed first? And then we can ask, what about the order? So what I'm going to do is we start with the independent particle model, and the mean field approximation was this box. Now I'm going to add in some residual interactions between those outside 2 particles, only between those 2. And that's in effect not included in the independent particle model. Just to jump ahead. These residual interactions, they actually dominate the evolution of structure. And there are a number of important effects. One is pairing, which we actually won't talk about too much in, well, we will talk about it in one sense. That has to do with 2 identical nucleons whose angular momenta add to 0. Okay, and we'll see why that is important in a few minutes. Another is a proton-neutron interaction, which turns out to be the most important thing determining how structure evolves when you change the number of protons and neutrons. And there's the monopole component of the pair-PN interaction, which we'll see changes magic numbers. So we talked about that a little, that the magic numbers far stability can change. That's primarily due to something called the monopole component. We'll talk about that. Okay, so we're going to have a Hamiltonian, which is H. H0 is just the independent particle model Hamiltonian, and H residual is the stuff we're going to add in. Now we're going to talk about a 2-particle system, and so we're only talking about the interactions between those 2 particles. So H residual is just H12, particles 1 and 2, and it's a function of the distance between them. Okay? So first question now is we're going to consider a particle with angular momentum J1 and another with J2. And the first question is what total angular momentum can be formed. The second one is what are the energies of those states. Wow, I don't need to show that. Okay, so let's consider which angular momentum can be formed. So imagine this is the angular momentum of one particle. I could in principle add another angular momentum like that to get a sum, which is the sum of the 2. Or I could add another particle going off in a different direction. So imagine this first one is a particle going around the nucleus like that, another is going around like this, and so its angular momentum is like that, and the sum is that. Or I could do this, that other one was supposed to have disappeared, but okay. Or I could do this, okay? All right, so there's several combinations. So, J1 plus J2. If J1 and J2 are different, then the 2 particles are in different orbits, and the Pauli principle has no effect. So that means I can form all states from J1 minus J2, that would be this, to J1 plus J2, that would be that. That's a trivial case. The interesting one, for example, J1 is 3, it should have been 3 halves actually, and J2 is 5, but let's just call them 5 and 3. I can form everything from 2 to 8. Okay, the interesting case though is when J1 equals J2. That is when I put two particles in the same orbit. This is what happens when you look at a nucleus which is magic in protons, magic in neutrons, and you add, say, two neutrons. They will go in the same orbit. So J1 will equal J2. The answer is that the only elements you can form are J equals 0, 2, 4, and so on up to 2J minus 1. That's obvious why you can't go beyond 2J minus 1. If you ask, what about forming an angular number 2J, that would be that. But then these two particles would be in exactly the same magnetic substate that would violate the Pauli principle. So it's obvious you can't, it's obvious you can't have 2J plus 1. What about 1, 3, and 5, and so on? Well, there are many ways of determining which J values are allowed. There are fancy ways involving group theory. There are other brute force ways. The easiest is to use something called the M scheme. I've introduced a new notation here. These red circles were slides that I was not going to discuss, but they would be there for completeness. The red circles with circles around them means that I've sort of changed my mind and I will discuss it. So let's illustrate the M scheme. Are these numbers readable at the back?
Yes.
Yes.
Okay. So let's consider two particles in an F7 halves orbit. This notation, by the way, with the superscript, that means whatever the superscript is, that many particles in that orbit, and this is the total J. So what we're going to do is look at the magnetic substates these particles can occupy, and then ask which ones are allowed. So I can do it in any order, but it's convenient so that I don't forget any, to use some sensible order. So I'm going to put particle 1 in a 7 halves magnetic substate. Right? It's J7 halves, so that's the highest magnetic substate. So what about particle 2? I can't put it in 7 halves. That would violate the Pauli principle, right? I can put it in 5 halves though. I can put it in 3 halves, I can put it in 1 half, minus 3 halves, minus 5 halves, minus 7 halves. Now let's add up the total magnetic quantum number for those cases. 7 halves and 5 halves is 6. 7 halves and 3 halves is 5, and you can probably with a calculator find out that these add up to 6, 5, 4, 3, 2, 1, 0. Okay? I can't do any more cases with this particle in 7 halves state. So now I go to the 5 halves. I can do 5 halves and 7 halves, but I've already got that there, and these are indistinguishable identical particles, so that's the same state. I can't do 5 halves and 5 halves because of the Pauli principle, but I can do 5 halves and 3 halves, 5 halves and 1 half, 5 halves minus 1 half, 5 halves minus 3 halves, 5 halves minus 5 halves, and I can do 5 halves and minus 7 halves. I don't write that, and I'll tell you why in a second. So let's look at what angular momentum these add up to. 5 halves and 3 halves is 4, and 3, 2, 1, 0. Now 5 halves and minus 7 halves would give me a minus 1. I don't write that only because if I did all of the cases, the table would be absolutely symmetric with positive numbers and negative numbers. And so it's just easier not to bother. Okay? That exhausts the possibilities of 5 halves. Now I do 3 halves. 3 halves and 7 halves is already used up here. 3 halves and 5 halves is already used here. 3 halves and 3 halves is forbidden. So 3 halves and minus 3 halves and 1 half, that gives you 2. 3 halves and minus half, 1. 3 halves and minus 3 halves, 0. And then the only other case is 1 half and minus 1 half, which gives you 0. So these are the total number of allowed magnetic substates for this two-particle system. Now, how do you know what J values? That's easy. You look for the largest n. The largest n is 6. So what does that tell you? That tells you you must have a J value at least 6, because a J value of 5 or 4 doesn't have a magnetic substate of 6. And you can't have a J value larger than 6. You can't have 7, because it would need a magnetic substate of 7. So the fact that the largest magnetic substate is 6 tells you there must be a J equals 6. Now, J equals 6 state has magnetic quantum number 6, 5, 4, 3, 2, 1, 0, minus 1, minus 2, blah, blah, blah. And so that uses up this group of magnetic substates. Now I look at the highest magnetic substate left, and it's a 4. By a similar argument, that means I need a 4. and that uses up these, and then a 2 is 0. Clear? So from that you deduce the 2 particles in F7 gives you 0, 2, 4, and 6. Is that clear to everybody? Is it not clear to anybody? Yes?
It's not 100% clear to me that it's really a group and not arrangement. I mean, you're picking the terms.
No, I've done all possibilities here.
I mean, for example, 7 half, 3 half gives dimension 5. So this would.
Which one are you looking at? 7 halves?
And the second one, the second column is dimension 5. So you choose to put it together with 6 and exclude it from another arrangement.
Okay, fine. I chose it so it would be easy for you to see. If you choose any other order, you're still going to have only one magnetic substate 6. That means you must have a J equals 6. That J equals 6 state must have a J equals 5 magnetic substate. So that requires this 5, and there's no other 5. So there can't be. So you can do it in any order you want. I guarantee you if you do it in a different order, you'll forget something. But well, maybe not for 2 particles, but try it for 6 particles. Okay? So it's not picking and choosing. This is arbitrary. I could have used this 6, this 5, this 4, this 3, this 2. I could have. There's nothing special about this particular association. It's just a way of counting. Good question. Okay. Okay. So now we know what spin states are allowed. Let's ask about the energies. So here I have a particle in orbit J1, a particle in orbit J2. Their total angular momentum is J. And notice what we're talking about here. We're talking about an angular momentum J1, an angular momentum J2, and a total angular momentum J. There are several states here, different J's depending on this angle. So 2 things are important. First of all, with no residual interaction, there's no reason why these levels should have different energies. So they will all be at the same energy. Now if I go back to the data on lead and polonium and tellurium, you see that that's not correct. So that immediately tells you we need some residual interaction. Second thing you see is the only thing that's different about these different J states is the angle between the angular momentum. So the only thing we need to think about is the angle between the residual interaction. These levels will split, and you will get different J values at different energies. And it's our job to figure out which one will be lowest. But just remember, the only thing that's different is the angle between the orbital planes. Okay, so this looks complicated, but we're not going to use it really. The shifts in energy are the matrix elements of 2 particles interacting with this residual interaction. And that can be written as a reduced matrix element. And you can put in wave functions and radial and harmonic oscillator, circle harmonics. And you can blah, 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 and do all that sort of stuff. The radial equation has no effect whatsoever. It's just equivalent to a change in scale. Everything depends on the angles. And we're not going to solve this. We're going to make physical arguments and get the result. But first we have to decide what H12 is. What is this residual interaction between 2 particles? So, it's on the bottom there. I was going to ask you what you think might be a good choice. The nuclear force is short range and attractive. Right? What's the shortest range force we can have? I'm old, I can't hear very well. What's the shortest range force there is? Somebody turn on their microphone and say something. What's the shortest range force? Yeah, but what's the mathematical form of it? I mean, the shortest possible range force you could have. What? Good. Delta force. Okay? So we're going to assume a delta force. Now some of you who ask questions are going to say to me, well, come on, that's not very realistic. And the answer is yes, you're right, but it works extremely well. It's one of these examples Absurdly simple assumption that works beautifully. Okay, so this is what a delta function looks like in spherical coordinates, radial and angular. Radial part's just a constant, so all we're going to look at is the angular effects. And by the way, that's a great simplification that often happens in nuclear structure calculations. Okay, so we only need two ideas only. That the nuclear force is short range and attractive, and we've already built that in by assuming a delta force, and the Pauli principle. And the argument is really, really beautiful and elegant. So let's think about what we're talking about. We're talking about two particles here, and they can have different orbital planes relative to each other. Which is going to be the strongest, so it's an attractive interaction, so it's going to lower the energies. Which orbits, which angles, will give you the lowest energy? So it's clear that you'll get the lowest energy with a delta interaction when the particles are closest to each other, right? Because they're not going to always cover. Yeah. So there are two cases. One is they're going around together, right? Which gives you the maximum J. Or the other case is they're going around, this is hard to do. I can usually go around once before I get in trouble. They're going around like that, in which case their wave function clouds overlap. That's the minimum J. So the lowest energy, we already know, just from that simple argument, it will either be the minimum J or the maximum J. So now which one will it be? Anybody want to guess? Yes?
You can't have the spinning in the same direction.
Sorry?
I don't think you can have the spinning in the same direction.
Because? Very good. So they can't spin in exactly the same direction, but they could be in very close orbits.
But it's not a meaning.
It's not what?
It's not a meaning.
That would be a pretty attractive interaction.
But compared to the other alternative.
Well, we're going to see. Okay, in parentheses, you're right, but the reason is more subtle. Okay, so what's going to be the lowest energy for two particles in the same orbit? I've drawn it here for two different orbits, but I'm talking about in the same orbit. Lowest spin or the highest spin? Sorry?
Zero spin.
Yeah, that's a corollary of your previous argument. Okay, the answer is the lowest spin, 0. And how do you know that? Well, you know it because you've seen the data. I've shown you the data on these nuclei, and the ground state's always 0 plus. But now we're going to find out why. The question is, why is it 0 plus? Okay, to do that, I want to decompose these angular momenta into an orbital part and a spin part. So I write the orbital part as the orbital angular momentum of the first particle plus the orbital angular momentum of the second vector sum. And the S, the intrinsic spin, is 1/2 plus or minus 1/2 equals 1 or 0. Okie dokie? Okay. Now, I have to make a comment about the Pauli principle. Pauli principle says no two fermions can be in the same place. But that is equivalent to saying the wave function must be antisymmetric. And you probably know this, but I'll just go through it. Suppose I have a wave function which is a function of some distance r. And if the wave function is antisymmetric, it must be that the wave function at distance r is equal to minus the wave function at minus r. R, in our case, is the distance between the two particles. Now, suppose the two particles are in the same place. Then r equals 0. Then this equation says that psi of 0 equals minus psi of 0. But the only way that can be true is if psi is 0. So this anti-symmetric condition is equivalent to the Pauli principle. The wave function vanishes if the two particles are in the same place. Okay, clear? All right. Now, we divided the wave function into its orbital angular momentum and a spin. And so the anti-symmetrization applies to the product of the spatial part, that's the orbital angular momentum, and the spin part. That has to be anti-symmetric. Okay, there are two cases. And this is one of the most important slides in all of nuclear physics. Okay, either spatial part is antisymmetric and the spin part is symmetric, or spatial part is symmetric and the spin part is antisymmetric. What do we mean by symmetric and antisymmetric for spin? If the two spins add, that's the symmetric combination, and if they subtract, that's antisymmetric. So symmetric corresponds to S equals 1, antisymmetric corresponds to S equals 0. So the two cases are S equals 1, the two intrinsic spins of the nucleons adding, and an antisymmetric spatial part, or a symmetric spatial part and the two spins pointing the opposite way. Okay? Let's consider these two cases. Let's consider this one first. So if the two intrinsic spins of the nucleons are in the same direction, I mean symmetric, then the spatial part has to be antisymmetric. If the spatial part is antisymmetric, we have this condition, which means that the wave function vanishes when the two particles are in contact. But we've assumed that the interaction is a delta force. Delta force only acts when the two particles are in contact. So imagine you're a delta force, and you're looking at these two particles and you want to have some effect on them. And the only place you can have an effect is when they're in contact, but when they're in contact, the wave function is 0. So there's nothing you can do. You're out of a job. So the delta force can have no effect, because the only place the delta force acts, there's no wave function to act on. It's like shadow boxing. Okay? So, if you have the two nucleon spins lined up, a delta force produces no effect. Okay? Is that clear? The other case, S equals 0, is simple. The spatial part is symmetric, there's no restriction, and so you can have an effect. Now let's put this in practice. Let's do a case for two particles in a G9 halves orbit. I can have two cases. I can have S equals 0, which means I have a G9 half G is L equals 4. So I can have orbital angle number 4 and 1/2 like this, and then orbital angle number 4 and 1/2 like this. That's S equals 0. Clearly this gives a total angle number J equals 0. The other case, which I've drawn slightly incorrectly, is 4.5 and 4.5, giving 9, but of course 9 isn't allowed anyway, but I can make this at a slight angle. That would be S equals 1 and J equals 8, and so these are the two cases. We know that this case, the delta function will have no effect. In this case, it will have a big effect, and so that tells us that the 0 plus is going to be the lowest. And the 8 plus actually will be the highest. You'll notice the 8 plus, this is a real calculation. The 8 plus is lowered slightly, and that's because this approximation here where I drew them parallel is not quite true. Okay, so now we have derived the fact, without actually any calculation at all, that if you have two particles in the same orbit, the lowest state they can couple to will be 0 plus. This fundamentally is the reason why all even nuclei have 0 plus ground states. Okay? You have very complicated situations when you have many valence particles, but if you trace it all back, it all comes back to this. Okay? Here's a cartoon of what's going on. In the S equals 0 case, the two particles are going in opposite directions, and their wave function clouds overlap. When the two particles are going around together, you might think that they would be close to each other and interact strongly, but the Pauli principle actually forces them to be on opposite sides of a radius and their diameter. And so they're actually as far apart as they can get. And that's why the 8 plus is the highest. Okay, now this is a cartoon, but it actually is shown by real calculations. These are calculations for two particles in an F7 halves orbit, and this is the radial distance, this is the wave function amplitude. In the 0 plus state, there's a huge amplitude here. As you go up and spin, the wave function spread out because the particles are orbiting far from each other. Okay, now I did it all just by arguing using the Pauli principle. There are real formulas, okay, and you can use these formulas and calculate, and you get results like this. I've only done the case for equivalent orbits. You can do exactly the same thing, and there's actually something covering it here, for non-equivalent orbits, and it's a very good exercise to try. And if you take, say, a particle in d5 halves and another particle in h11 halves, they can couple the spins 5 plus 11 is 16 halves. They couple from 8 to 3, and either the 3 or the 8 will be the lowest, and you use this argument with the S's to figure out which it is, and it works. Okay? There's one other feature I want to talk about here. Notice that the lowering of the 0 plus state is more the higher the J value. And in fact, if I go back here, hidden down here, it actually goes as 2J plus 1. And you can see that here as well. It goes as 2J plus 1. Okay, so why is it that the 0 plus state is lowered more the higher the angular momentum? Anybody have an idea? Just like tin scanner task, there's no such thing as a stupid question, there's no such thing as a stupid answer. Anybody have an idea why? I'll give you a hint. Something I've said is an approximation, but I haven't told you that it's an approximation. Maybe that's not such a great hint. It only has to do with the angles of the orbits. Anybody have an idea? No? Would you like me to tell you? Okay. Oh, by the way, note that R42 is less than 2. So, okay, I forgot this was going to come. So this very simple treatment of residual interaction accounts for the and that the 0 plus level is lower more the higher the J. Okay, here's that effect just showing up again. Okay, and the question is why? The answer has to do with quantum mechanical localization. What I mean by that is the following. I've talked about a particle going in some orbit at some angle around the nucleus. But that's not what happens. That's a semi-classical approximation. In practice, the wave function in angle is fuzzy. Okay, and the wave function is spread out over a range of angles. What's the range of angles? Well, let's consider this low J orbit and this angular momentum vector. So the particle is going around like this. Okay? But the wave function can spread out. It doesn't have to be centered along this direction. It could be over here a little, it could be over here. But it's limited basically to halfway between these two vectors to halfway between these two. So the wave function is localized in angle. Now let's consider a high J state. If you consider a high J state, there are more magnetic substates. You still have 180 degrees. And so the localization is more intense. The wave functions are more localized in angle. So now think about two particles going around the nucleus. If they can fluctuate in angle like this, as they can for a low J orbit, they're not going to be as close together on average as they could be, and the effect of the delta force will be less. On the other hand, if they're constrained to be very, very close to each other in angle, they're going to interact more. And so the higher the angular momentum, the more localized the wave functions are along a specific angle, and the more they'll interact. So more magnetic substates, greater localization, greater spatial overlap, lower energy. Clear? Okay, I want to extend, oh my God, is that 3 or 315? 3, okay. I want to extend the interacting, the independent particle model using this result to a few more nuclei. Let's look at calcium 43. It has 3 particles in an F7 halves orbit. Okay? First question is, what angular momentum do these 3 particles add up to? And it's a very nice exercise you can do with the M scheme if you want. The answer is the possibilities are 15 halves, 11 halves, 9 halves, 7 halves, 5 halves, 3 halves. Now let's consider these different cases. Suppose the total angular momentum is 7 halves. Total angular momentum of all three particles combined. If the angular momentum of all three particles is 7/2, it means the angular momentum of 2 of them must have coupled to 0. Right? I've got 3 that add up to 7/2. If that means that 2 of them have to couple to 0. For all the other cases, 15/2, 11/2, 9/2, 5/2, and 3/2, there are no pairs coupled to 0. Right? If I want to make a 9/2 state out of 3 7/2, I can't couple 2 to 0 because then all I'm left with is 7/2. So in all of these cases, the only one where 2 particles are coupled to 0 is the 7/2. We know that 2 particles coupled to 0 experience a strongly attractive interaction, and so the 7/2 will be the lowest. Okay? So, well, that just says this. So the 7/2 must be lowest, so we would predict that calcium 43 would have 7/2 minus ground state. Okay? You can now take this picture, which I showed you yesterday, and predict the ground state spins of all these nuclei as well. So we've expanded the extent of the independent particle model with residual interactions to take account of quite a few more nuclei. Okay. All right, up to here. Any questions here? Yes. Turn on your machine.
Sorry. Maybe I don't need it. Turned on.
The people behind you.
Okay. So at some point from quantum state characterized by the quantum number j, you went to quantum states characterized by numbers L and S. But if you have a spin orbital Hamiltonian which contains spin orbital term, so this Hamiltonian will not commutate with L and S, so somehow, I mean, in literature they say that this is not good quantum numbers, but I don't like this. I say they don't just commutate with the Hamiltonian. So is this correct what we do here?
So you're absolutely right. Making this approximation of looking at the angular momentum in terms of L and S is an approximation. Okay? But as you see, it works pretty well. And so that's kind of the justification of it. You can do it much more rigorously. I showed you the analytic formulas. Those analytic formulas are derived without any assumptions like that at all. Okay, but they give exactly the same results. Okay? Other questions? Okay. So now let's move beyond magic nuclei. What about nuclei with many valence nucleons of both types? And what about cases where the particles can occupy more than one single particle level? So far we've said that neutron, let's say, is in F7/2, and the proton in F7/2, or the proton in H9/2. But not that the neutron could occupy 2 or 3 different orbits. It can, right? So what about that case? We can, in general, we can form many states of a given angular momentum. When we have 2 particles in F7/2, we could form 0, 2, 4, and 6 angular momentum. 1 0 plus state, 1 2 plus state, 1 4 plus state, 1 6 plus state. Once we have more particles, maybe we can form 2 2 plus states. Or 6 plus states, or whatever. And then we're going to have a situation where we have several states of the same spin. Those states will interact with the residual interactions. They will mix, and we'll get a complicated situation. So, once you can form more than one state of a given angular momentum, you have to take into account interaction of those states. The result of that is the emergence of collectivity due to this mixing. I want to look at the problem first and then some solutions. So here's the problem. As the number of valence nucleons grows, the number of ways of making states of a given J grows hugely. Whatever number of ways you can make a state of a given angular momentum, those states form a kind of system. They can interact with each other. You can have mixing effects, and the resulting wave functions will be some mixture. The wave functions will be mixtures of those basis states. So, what I want to do, okay. So let's consider some cases. Let's consider a case where we have only 2 nucleons and they can occupy a d5 halves orbit. The question is, how many 2 plus states can we make? I want someone to answer that without looking at this number. How many? Could someone please say the number 1? Could someone say it? Somebody. Thank you. Do you all understand why it's only 1? With the end scheme, if you look at the 2 particles in the d5 halves, you can form angular momentum. Well, why don't you tell me what angular momentum you can form? 2 particles in a d5 halves orbit. What angular momentum can you form? Someone turn on their microphone and tell me. Thank you.
0, 2, and 4.
Okay, how many 2 plus states? 1. Okay, good, wonderful. So we form 1 2 plus state. Let's take a slightly more complicated case. 4 particles that can occupy 2 orbits. How many ways can we make a 2 plus state? Well, let's see. We could put 2 particles in d5 halves and couple them to angular momentum 2. And we could put the other 2 particles in g7 halves and couple them to angular momentum 0, right? If you have an angular momentum 0 and an angular momentum 2, that adds up to angular momentum 2. So that's a 2 plus state. We could do the opposite. We could put 2 particles in d5 halves, couple them to angular momentum 0. Put 2 particles in g7 halves, couple them to angular momentum 2. Add 0 and 2 and you get 2. That's another way. We could put 2 particles in d5 halves and couple them to angular momentum 4. 0, 2, 4. And then we put 2 particles in g7 halves, couple them to angular momentum 2. And then have 4 minus 2 and you get 2. We could put 2 particles in d5 halves, couple to 2, and 2 in g7 halves, couple to 4, and again net 2. We could have 4 and 6 and net 2. If we have 2 particles in different orbits, we can form j equals 1. And we can form j equals 1 here and add that up to j equals 1. Or we could have 2 particles in d5 halves, couple to j equals 4, 2 particles in g7 halves, couple to j equals 4, those can also couple to angular momentum 2. And I probably have not included all of them because I probably didn't include some of this cases with 6. But maybe I did. Anyway, I can make at least 7 states. Is that clear? Now if I have a nucleus with these 4 particles occupying these 2 orbits, and I can make 7 2 plus states, one of them will be the lowest. But in all probability, the wave function at lowest will not be just one of these components, but it'll be some linear combination, some mixture. And that will depend on the details of the interactions. Now, I want to consider another case. Let's look at samarium 154. Samarium has 62 protons, 92, this has 92 neutrons. The nearest close shell is 50, so there are 12 valence protons. The nearest close shell is 82, so there are 10 valence neutrons. So 12 valence protons fill the 50 to 82 shell. 10 valence neutrons fill the 82 to 126 shell. Of course, in principle, we could open up lower shells or go to higher shells, but let's just consider these shells. Okay? How many 2 plus states can we make? Subject to the Pauli principle. Now, I'm not going to go on until I hear at least 3 estimates. How many 2 plus states can I make? I'm going to sit down and take it now. 100. Good answer. Good answer. 100 2 plus states. I want another answer. We're about to get an answer.
10 to 52.
10 to what?
52.
10 to the 52nd power? Really? Wow. Okay, I want... What are your names?
Harry.
What?
Harry.
Harry and... Okay. How many think Harry is closer to the right answer? Raise your hands. Ah, so I can see them.
I don't think I'm close to the right.
How many think that Vesale is closer to the right answer? Oh, you don't have many friends. Oh, he's us there. Okay. I want a third answer.
1,000.
Who said that? How many think he's got the right answer? You have one friend. Okay. So the answer is, let's see. You're closest. You are next closest, and you're the furthest. But you had the right idea. The answer is 3 times 10 to the 14th. So you just went a little too far. And you didn't go quite far enough. And you were wrong. Okay, that's a lot of states. To solve this problem, you have to diagonalize the matrix, which is 3 times 10 to the 14th by 3 times 10 to the 14th. I'd like you to do that for homework. Okay, the largest matrices we can diagonalize, even with fancy Monte Carlo techniques, is like 10 to the maybe 11th by 10 to the 11th. Takes gazillions of hours of supercomputer time. We just can't deal with this. We have to somehow approximate things. Okay, so this is the fundamental problem facing us. And you can see this here. I've shown this slide already. I'll just reiterate. Here's the nucleus with 2 valence nucleons. Here's the nucleus with 2 plus, I can't even get that number, 68, I guess. So it's got like 16 valence nucleons. And what do you notice? You notice the energies come down. The energies change from this monotonic sequence, which we just derived, thinking about residual interactions, to a completely different sequence where we have multiplets and where we have a different order entirely. It's not monotonic. And this turns out to be a collective phenomenon. How can we understand this? This just is a reminder slide. 2 valence nucleons, a few valence nucleons, more valence nucleons, and many. R42 here is on the order of 2. Oh. Yeah, R42 here is about 2. And R42 here is about 3.33. Okay, so there are 2 approaches. Advanced methods at the levels of nucleons and their interactions, but the really rigorous way to do it only works up to about mass 12, so that's not going to help us too much. Collective models that look at the many-body system as a whole, and instead of looking at what the individual nucleons are doing, they treat the nucleus as a thing and ask, what can it do? Can it vibrate? Can it rotate? Whatever. So think of it as a balloon. Maybe it can vibrate, or a balloon shaped like a cigar, can rotate, things like that. So that's the approach of collective models, and that's what we're going to look at. So we're going to follow the second route, but then in the last lecture we're going to come back and look at the microscopic drivers of structural evolution. In other words, why the effects we see here occur in terms of particle interactions. So the development of collective behavior in nuclei comes primarily from correlations among the valence nucleons. The wave functions of the independent particle model are mixed. This leads to a lowering of collective states and to enhanced transition rates. Now, I haven't proved this to you yet. I'm going to. Okay? In fact, the second part here will be, somebody asked me a question at the end of first lecture, I think it was it you? Yeah, about enhanced transition rates and how they come about. So I'll talk about that. And so I'm going to look at the mixing of states. Okay. In any many-body system, you can generally make states of a given angle in more than one way. I'm just repeating myself. In the simplest model, these are independent, separate states. In reality, they will mix. And so I want to consider quantum mechanical mixing. And so there's really nothing useful in this slide. So I want to consider quantum mechanical mixing. And this mixing is the essential key to understanding anything about collective behavior. Okay, so this is just pure textbook. I want to consider 2 states with energy E1 and E2. I use Arabic numbers for the unperturbed states, Roman numerals for the perturbed. They have an energy separation of delta E unperturbed. And I'm going to allow these two states to mix with some interaction V. Okay? The final states, you know the two states that mix, I hope you know this, will always repel each other, right? They will be further apart after mixing. All of you know that? Okay. And so the shift in energy is delta S, delta ES, that's for shift. And the mixed wave functions, I use psi's for the mixed ones and phi's for the unperturbed. This wave function will no longer be just this. It'll be this plus some amplitude of this. So alpha phi 1 plus beta phi 2, alpha squared plus beta squared is 1. The wave function of this has to be orthogonal. It's minus beta phi 1 plus alpha phi 2. Okay, and if you work through the math, which is just diagonalizing a 2 by 2 matrix, this amplitude beta is given by this, and it's a universal result that doesn't depend on any details. It only depends on the ratio of V to the unperturbed separation. I call that R, 1 over R. So R is the unperturbed separation divided by the matrix element, the interaction stream. And so this amplitude B just simply depends on R. The further the states are apart, the larger R will be, and the larger R will be, the smaller beta will be. The closer the states are together, the smaller R will be, and these will be smaller and this will be bigger. Okay? If the two states are degenerate, same energy, then R will be 0, so you have 0 there, square root of 1 squared is 1, 1 plus 1 is 2, beta will be 1 over the square root of 2. Okay, here is a table just with some examples. Suppose R is 20. In other words, the states are far apart. Okay, then the shift over the unperturbed is very small. The wave function is very small. The wave function amplitude. And here I have a calculation for a separation of 100 kilovolts. So R of 20 means the matrix element is 5. Okay, and the shift is 1/4 of a kilovolt. On the other hand, if I have R of 0.2, then the shift is actually almost 5 times the spacing. The wave functions are almost completely mixed, and the shift is, in fact, in this case, like 452 kilovolts. Okay? And you can make a nice plot of these results and see how the effects go. Okay, now that's for 2 levels. Now, we might have 3 times 10 to the 14th levels. So what happens when you have lots of levels? Well, if you have lots of levels at various different energies and they're all going to mix, you're going to get a complicated thing, and you will get some resulting states which will have various energies and various wave functions. In general, that's a very complicated situation. I'm going to look at a toy model here, which is very simple, but which captures the essence of the real situation. So I'm going to consider n levels, all of them degenerate, all interacting with the same matrix element. What happens is all of them except one go up in energy by V, and one comes down by n minus 1 times V. And the wave function for this state is a perfect linear combination of all of these unperturbed states with the same amplitude in phase. To jump ahead to your question, the fact that these are all in phase means that in matrix elements leading to the BE2 value, you're going to get many contributions which will add up coherently. Okay, so you always get the lowering of one state, and its component wave functions are equal and in phase. And please try to think about this carefully. It's one of the most important and general concepts in all of many body physics. What happened? Okay. So the consequence of this is, whenever you have many states that can mix, one or more will come down low in energy, and they will have enhanced transition rates. I haven't proved that yet, but I will. Okay? These are the collective states. Collective means the various components are coherent. you see that. Okay, so what I want to do now is describe a couple of situations. The first is when we have a few valence nucleons, let's say 6 to 16 or so. Now I'm just going to tell you what the answer is. I'm not deriving it because it's complicated to derive it, but from what you've seen, you can understand the effects. You will have states that have come down in energy, at least some of them, from where they would be if there were no mixing. Okay, and I don't really want to go back. I don't know. There we go. Well, okay, yeah. This is the effect of coming down in energy. This is this buildup of collectivity. These states are simple, they're just two particles in a given J orbit. This, with about 16 or so valence nucleons, this wave function will be a complicated mixture of maybe 100 or 200 or 300 or 500 unperturbed 2+ states. Okay, excuse me for this. Okay, so when you have on the order of 10 valence nucleons, you can think of the nucleus as like a spherical balloon. But a balloon is squishy and you can squeeze it, and so it can oscillate, and you can get quadrupole shaped shapes. Take up a spherical balloon and squish it this way and squish it this way. And so you can get vibrations, you get oscillations in shape. Those oscillations carry angular momentum 2, and they're, you know the word phonon? So it's a phonon or a boson, it has integer angular momentum. It's a vibrational excitation. Okay? Now, since it's integer angular momentum and a phonon or boson, Pauli principle doesn't apply. It means you can superimpose more than one of these. And you can get 2 phonon states, and 3 phonon states, and 4 phonon states. How do you know which angular momenta are allowed? Well, again, the M scheme comes to the rescue. You'll notice the red dot doesn't have a circle around it, and that's because the homework is what angular momenta are allowed for 3 quadrupole bosons. If you go through this table, you will find that for 2 quadrupole bosons, each with angular momentum 2, the M scheme allows you angular momenta 0, 2, and 4. I want you to tell me, if you want to do it, it's up to you, what angular momenta are allowed for 3 quadrupole bosons. Here is a great example of a vibrational nucleus. It's cadmium-110, based on a number of experiments, many of them done by Young-Jolie and Cologne and colleagues. You have a ground state, which is 0+. And here I write the number of quadrupole oscillating phonons. Ground state has 0. First 2+ state has 1. At about twice that energy, because you just add the number of phonon energies, you get a triplet, 4, 2, 0. Remember in the previous slide I said the 2 quadrupole bosons, phonons give you 0, 2, 4. At about 3 times the energy, you have 6, 4, 3, 2, and 0. So there's the answer to the M scheme. You get those 5, I'd like you to do it. You go to the next one and you get another multiple and so on. Some of these multiples experimentally are not known completely. And here's a beautiful example of a near harmonic vibrational nucleus. Gamma ray transitions. Again, I'm not going to derive this, but a gamma ray can create or destroy a single phonon. So that means that you can have a gamma ray transition from this first 2+ state with 1 phonon to the ground state, or from this 4+ state or 2+ state to this 2+ state. That destroys 1 phonon from n equals 2 to n equals 1. But this transition from a 2 phonon state to the ground state is forbidden. So that's a characteristic signature of a vibrational nucleus. Okay. Deformed nuclei. What's different about non-spherical nuclei? They can rotate. A spherical quantum mechanical object can't rotate. You can't, if it's perfectly spherical, you can't determine one orientation from another. Okay? Should we take a break, or should I quit soon, or what should we do? I probably should have asked you to go on a break early. Do you want a break?
Yeah.
Is that a yes?
For me, yes.
Okay. Who wants a break? Who doesn't want to? Okay. So what's different about the deformed nuclei is they can rotate. A spherical quantum mechanical system is the same in all directions, so there's no meaning to the concept of rotation. But something that's shaped like this can rotate. Now, there's nothing that stops a deformed nucleus from also vibrating. Okay? All of you in school studied about vibrating, deformed rotors and things like that, right? Did you also study about vibrators? Okay. Anyway, so deformed nuclei I can't see that, there it is, can rotate and they can vibrate. Okay? And so the levels of deformed even nuclei will consist of the ground state, some vibrational modes, like the phonons we just saw for spherical nuclei, and rotational sequences called rotational bands built on top of them. Okay. A subtle yes?
Are you going to explain what is the beta?
Yes. Just a subtle comment about deformation. Ground states of all even nuclei are angular momentum zero. Angular momentum zero wave functions, that the angular part of the wave function corresponds to the spherical harmonic y0, 0. And so that's spherically symmetric. So how can the nucleus be deformed if it's spherically symmetric? Okay, it's a very subtle point. I'm not going to answer it completely, but the basic idea is when we talk about a deformed nucleus, we're looking at the nucleus sitting there in its own frame of reference. When we're talking about the angular momentum 0 plus, we're talking about an angular momentum measured in the lab. And since this nucleus is just freely sitting there in space, it can be in this position or this position or this position or this position. And the final wave function will be a superposition of all of those, which will be spherical. So that in the laboratory it will look like a spherical object, but in the body fixed system, it can be deformed. That's a quick answer to actually a very subtle question. Okay, deformed nuclei, rotational spectrum. I think I already said this, but I can't remember if I did. The angular momentum, the energies for a deformed rotor, this is just the solution to the symmetric top. They go as I times I plus 1. Here I use I for angular momentum, I usually use J. And this term here is h bar squared over 2 times the moment of inertia. So the moment of inertia is related to the deformation of the ellipsoid. And the larger the ellipsoid, the lower the energy of rotation. Okay, let's look at this formula for a minute. I times I plus 1, or J times J plus 1, is the angular minimum state times the angular minimum plus 1. 0, so for the 0 plus state, that's 0 times 1. Can anyone calculate that? What do you get? 0 times 1? Good. What about for the 2 plus state? 6. What about for the 4 plus? What's 20 divided by 6? What's 20 times divided by 6?
81.
Very good. What about for the 6 plus state?
42.
Divided by 6 is? Get out your calculator. 7. Okay, so these are the predicted energies for a deformed rotor. Here's a non-typical example, but an interesting one. Nobelium 254. And you see that these energies agree very, very closely. Okay? Now, I want to just take a step back and talk about the philosophical point. This formula is an idealized formula. No nucleus is going to be a perfect rotor. But I want to talk about the value of paradigms like this. Okay? And so, here I have an imaginary level state. This rotational formula was first applied to nuclei in 1952, before many of you were born, before some of your parents were born. Okay, imagine that you're sitting in a seminar in 1951. Okay? And someone says, I measured these energy levels. Nobody would think to say, what? That can't be. Why isn't this 333? Because they don't know the formula at that point. So, without the rotor paradigm, you would look at these numbers and go, oh, okay. With the rotor paradigm, J times J plus 1, here I use J. If I call this 100, I get 0, 100, 333, and 700. So two things have happened. Because I have this paradigm, I immediately recognize that this is a rotational deformed nucleus. But more than that, I notice differences. What's this 3 kilovolts? What's this 10 kilovolts? So I immediately notice that not only is it a deformed rotational nucleus, but there's some other effect going on. Now, there are actually multiple interpretations of this effect, but can anybody think of why these energies would be a little lower than the rotor formula? Yes. Here's this formula. As the nucleus rotates, it stretches, the deformation increases, the moment of inertia increases, and this paradigm assumed a constant moment of inertia. So you immediately get evidence for something like centrifugal effects. So having a paradigm, even if it doesn't apply very well to real cases, this one happens to, is very valuable because you can identify first the structure of the nucleus overall, and secondly, additional degrees of freedom. Okay, here is a level scheme of a typical deformed nucleus. It looks complicated, right? Does it look complicated?
If you have to sleep with this scheme for 2 months.
If you what?
You have been sleeping in your head with this level 3.
Have you been sleeping with this? Okay, so let's look at this and see if we can understand it. There's a ground state which is spin 0, and a 2, 4, 6, 8, and here are the experimental energies. And what I've done here is normalize this. I've used this rotational formula. And I get 304, 639, 1096. You can see the centrifugal stretching. So this is a ground or equilibrium state and a set of rotational states. Okay? Now, what are these guys? Remember I said that a deformed nucleus, just like a spherical one, can vibrate. Okay? These are two different vibrational modes. Anyone have a, oh, can I borrow that cup?
Yes.
Is it filled? Is it empty? Okay. No, I want to. Okay. So here's a deformed nucleus. Okay, it's not actually tapered, but okay. There are two ways it can vibrate. It can go out like this. And notice that there's no angular momentum associated with that. The other thing it can do is go like this. Now that may not look like angular momentum, but it is, because I can equally well approximate this by going like this and rotating and rotating and rotating. So this kind of oscillation is equivalent to rotation around this direction. It's like this. So those are two modes. The first one is a change in the amount of quadrupole deformation. The variable we use to specify the deformation is usually called beta, and so that's called a beta vibration, and that's the one that starts with angular momentum 0, precisely because there's no angular momentum involved in this kind of motion. The other one is called a gamma vibration because gamma, can you see that? Okay. Because gamma is actually a variable that specifies the axial symmetry, and that gives a level which starts with 2+. On top of each of those, are rotational states. So this rather complicated looking level scheme is really pretty simple. It consists of a ground state, nucleus can rotate, a vibrational state which is changing the axial symmetry and can rotate, and a state, vibrational state that changes the elongation of the ellipse, and it can also rotate. Okay. Just to remind you of these three things we've seen: two valence nucleons, vibrator, and rotor. These are kind of the paradigms and benchmarks of structure. There's one more called 06 or Willett-John, but I won't go into that. Yeah, okay. So I'm going to end with this slide. So there really wasn't very much after the break. Maybe we'll discuss it. These are these BE2 values, these transitions from the 2 plus to the 0 plus. They go as the square of a matrix element. And this matrix element is very small for magic numbers. For the form collected nuclei, it's very large, and that is a consequence of mixing. Now, this is the question you asked me. You guys want to listen for 5 minutes more to see how that relates to mixing? Or should I stop? Okay. So, here is a derivation of the enhancement of these BE2 values due to mixing. So what I'm going to assume is that I have, this is an extreme toy model. Let's assume I have n levels, all degenerate, all mixing with the matrix element V. Okay? We know what happens. One level comes down by n minus 1 V. In other words, it comes down to here. But what I've done is I've drawn a lowering of it due to interacting sequentially with each one of these states. The wave function is a perfect linear combination of all of the unperturbed basis states. And because the sum of these squares of these coefficients has to be 1, A is 1 over the square root of n. Okay? Now I want to consider that this is the 0 plus state. Let's just say, assume these are 2 plus states. I want to calculate the transition rate from this 2 plus state to the ground state. So the BE2 value is just a statistical factor times the square of the matrix element. So what's the matrix element? The matrix element is between the 2 plus state and the 0 plus state. I keep the 0 plus state here. And here I replace the 2 plus state by its wave function. This wave function is a linear combination of terms that are all equal in amplitude. So I can replace this now by a sum A times the sum of the matrix elements from 0 plus 1 up to with phi I. Clear? Now I'm going to assume that each one of these unperturbed states decays to the ground state by the same matrix element. Now that's a stupid assumption. It's clearly not true, but I want to illustrate the point. So let's just do that. Okay, if that's the case, I call that strength W, then this matrix element, which is given by this, is just N, these are N states, times A, and this is W. So that's NAW. A is 1 over the square root of N, so this is the square root of N times W. The BE2 value is proportional, this is 2J equals 1, to this squared, so it's proportional to NW squared. So the BE2 is proportional to the square of any of these individual matrix elements times the number of states that mix. And so that means you get an enhancement to the BE2 value, therefore to the transition rate by a factor of n. Sumerian 154. Sumerian 154 has 3 times 10 to the 14th 2 plus states. This model would give an enhancement factor of 3 times 10 to the 14th. However, what we see here is an enhancement factor. These are sort of what you would get for a single particle of a couple hundred. So this model grossly exaggerates the effect. And the reason is because it's crazy to assume that all these matrix elements are equal, but it illustrates the idea. When you have collective wave functions, you have components that add up, and they add up before they get squared. Okay? And so therefore you get a coherent sum, and you get enhanced transition rates. Okay? So that's the origin of enhanced rotational transition rates. If I go back 10 clicks to here, these vibrational modes are also collective. Their wave functions will have a number of so their BE2 values for the ground states, low-lying states, will also be enhanced. They won't be as enhanced as much as the rotational states, but they'll still be enhanced. And so it's very typical in the form nuclei to get enhanced BE2 values, and the origin comes from simply this mixing of states and the fact that the components are in phase. Does that answer your question? And it's a fundamental property of collective states. One last thing. Relation of BE2 values to the nuclear shape. I'm not going to derive this, I'm just going to tell you. The quadrupole moment of a nucleus, that's a measure of the deformation, is given by some numbers times the deformation beta, that's the elongation of the nucleus, times some higher order terms. The BE2 value can be written in terms of the quadrupole moment and the Klopsch-Gordon coefficient this way, so it goes as q squared. So if you plug in the values of the Klopsch-Gordon coefficient for transition 2 to 0, you get 5 over 16 pi q0. Q0 is given by this. I'll ignore this second term here. And so that gives you this, which has a beta squared in it. And so if I solve for beta, I get that beta is some numbers times the square root of the BE2 value. So if I take measured BE2 values from the 2+ state to the ground state, I can extract the shape of the nucleus. And this is what you get in the rare earth region. And you'll notice a couple of things. First of all, you get large deformations on the order of 0.3. Secondly, you'll notice that around here you get maximum deformations. And why is that? The doubling magic nucleus down here is tin-132. The doubling magic nucleus up here is lead-208. This is just about mid-shell. This is the place where you have the most basis states that can mix, and therefore the most collectivity, and therefore the most BE2, and therefore the most deformation. And so this overall pattern is simply a consequence of the mixing of these wave functions. It also comes out as a consequence of the concept of seniority, but that's way beyond these lectures. Okay, so I think that's a good place. Yes, okay, so the next topic I'm going to cover next time is, so we talked about nuclei that are spherical, that are near magic numbers. We talked about vibrators, we talked about rotors. What happens in between? How do vibrators turn into rotors when you add more valence nucleons? And that leads to the concept of quantum phase transitions. And this is a topic which I put in because somebody asked me yesterday to talk about this. So, is that you? Okay, so next time. Okay, any questions? Don't forget your homework. Okay, you had a question also.
When we talk about mixing, now we talked about mixing between different 2+ states. Can states with different angular momentum also mix?
No. Well, it's very simple. Suppose you have a 2+ state and a 4+ state. Okay? And suppose you mix them. Then the wave function would have some amplitude for 2+ and some amplitude for 4+. That means it would not have good angular momentum. But angular momentum is conserved. Very simple.
I have another question.
Yeah.
You showed this nucleon nucleus,
Yeah.
and there you also had arrows between the states, and the arrows, the size of the arrows changed.
You mean they get thicker? Oops.
Yes.
Which one? Okay, this I took from some paper. These are gamma ray intensities that are measured. And as you come down this rotational band, they increase. Because you're also getting feeding from other levels.
So the numbers are the energies.
numbers are the energies, they're not the V2 values. Okay, and by the way, the white here is, this is an actinide, so it has a very high Z, and a level can decay by a gamma ray, but can also decay by emitting a conversion electron. Sorry?
I think this is done by other, and it's the automatic, if the symbol goes to some database, take the conversion coefficients and put them.
Yeah.
You just put, I have condition there, this goes to.
Yeah, exactly. So this is the measured gamma ray intensity, and this is the total intensity of that transition, including conversion electrons. But basically, the thickness of the arrow is the number of times this level decays. And what's missing here is all the feeding from other levels.
If I can answer. If you have mixing of several states, the thing you see in an experiment is mostly only the lowest, the state that's low. But there is no way of knowing how many states mixed in the first place.
In general, no. Well, you can do a calculation, some model that can give you an estimate. Experimentally, no, you don't. You can get a feeling for it by looking at how enhanced the transition rate is. A Weisskopf unit, by the way, is, I guess most of you know it, but it's sort of a measure of what would happen if you just had a single particle transition from one level state to the next. So if you have an enhancement of 200, that gives you an idea that you must have, obviously you must have more than 200. They're not going to contribute all equally, so it probably means thousands at least. If you have an enhancement of 6, like you do for gamma band to ground band transitions, it probably means something on the order of 10 amplitudes that are important. So you can get a qualitative feeling. You have another question? Yes?
So my question is, well, at some point you got this cup and managed to explain to us why we have angular momentum in the gamma, but we don't have maybe.
No, you got it right,
In beta. So at least it's, can you explain why we have, let's say, only even spins in the ground band and in the beta band, but in the gamma band we have odd and even without going into the dead functions? Because from the dead functions they come completely mathematically perfect and so on. Can you explain?
So can I give you a simple intuitive explanation?
Yes, please.
Okay, the answer is no. Sorry. If you have an intrinsic state, that's what we call the base states, of angular momentum 0, you only get the even spins. If you have any other intrinsic, you get all of them. And it comes from the symmetry of the wave function. The wave functions have to be symmetrized with respect to the particles going around this way,
that's okay.
or this way, and it comes from a phase factor, but I can't give you a simple intuitive explanation, at least not today, maybe tomorrow. Other questions? We have 1 minute.
Yeah, I have a final, maybe one question. I hope the lessons you will tell us how you go from a mesh of excited states into something you organize in bands. And you show, for instance, I think was this one with the rotational band and the 2 vibrational bands, but what you measure is really a mixture of these states. So the key point for an experimentalist is how to organize, how to get the patterns out of your
Okay. So you want to know? Well, let's go back to that for a second. So let's imagine that it's not presented this way, but that it's presented as 0, 2, 4, 6, 2, 3, 8, 4, 5, 0, 2, 6, 4, all in a column, right? How do I split that up into this and this and this? Okay. If I try to answer it now, it'll be confusing. I'll make some slides for next time. Who has heard of the Oliga rules? Oliga rules. Yeah, of course you have. Anybody else heard of the Oliga rules? Would you like to? Good. All right, I will introduce the Oliga rules and also some other ways in which we can understand that. Okay, good question. I wasn't going to go that much detail. Okay, I will. One more question.
No more questions? I think we have asked many questions today.
Okay. All right.
Thanks a lot. And
They have the same problem for tomorrow to ask questions in the beginning?
I would like, yes, and I would like that the ones that didn't ask questions try to prepare. Tomorrow and the following days will be also here. And I will put the talks in the Indico page, so please just check the
Can you send us a link